One of the applications of Dalton's law of partial pressures has to do when we collect gas products during aqueous reactions. And we call this collecting a gas by water displacement. And in the experiment, which is shown here, we get gas that's formed in a reaction, and it's pumped through and of course this is an aqueous reaction. This is zinc and HCl. The gas is then created, hydrogen gas, and it's pumped through a tube, which then goes into what's called a gas collection bottle. And really, the way that you set this up is you just take the bottle and you fill it with water, and you cover it, and then you stick it the open end down in the water, and then you remove the cover, which is usually a big glass plate. And then at the beginning of the experiment, it's completely full of water. And as gas is produced in the reaction, it begins to displace the water from the tank. And then what you have up in the space above the collection container is you have hydrogen molecules, which are the ones that are shown. See if I can get this to zoom. Nice, it just doesn't want to zoom for me. There we go. What we have is we have a then when I go to the laser pointer, it makes it small again. What you have is hydrogen molecules and water molecules and a mixture of gases up here. And it turns out, and we'll talk about this a little bit, but it turns out that the water vapor pressure is only dependent on temperature. So for example, at 25 degrees Celsius, the pressure of water vapor is 23.8 torr. And if you want to calculate the pressure of hydrogen, for example, that's been generated by this reaction, then all you need to know is what the total pressure is which is really just the barometric pressure. We look it up, and then we can subtract the water vapor pressure from the total pressure, and we'll have the pressure of the hydrogen gas. So if the atmospheric pressure was 760 torr, what is the pressure of hydrogen gas? Yeah, to do that, all you need to do is say pH2 is P total minus pH2O, which is 760 minus, and at 25 degrees it would be 23.8 torr, and those are both in torr units. 736.2 torr. And then you can use that, for example, in an ideal gas law calculation. To calculate perhaps the number of moles, right, of hydrogen that were produced in the reaction. So here's a table of water vapor pressures versus temperature. And I just want you to notice a couple things, that the temperature, as the temperature increases, the vapor pressure increases. Now, if you graph these, what you'll notice is initially the vapor pressure increase is fairly gradual, but as you get to higher temperatures, the vapor pressure increases exponentially with temperature. Another interesting thing to make note of is at 100 degrees Celsius, the water vapor pressure is 1 atmosphere. So this is actually not a coincidence that it's 1 atmosphere, because this is the reason why water boils and you get bubbles in it. What you're actually doing is you're heating the water hot enough that its vapor pressure exceeds the atmospheric pressure, and at that point bubbles form in the liquid, which are actually pure water vapor. Now, if you continue to heat water, right, beyond its boiling point, it can have much higher vapor pressures, and this is actually the way a pressure cooker works. That is, you seal the vessel and you boil water in it, and then it's able to reach temperatures higher than 100 degrees Celsius. And as it turns out, when you cook food cooks exponentially faster with higher temperature. So here's a problem where we apply idea of Dalton's law of partial pressure and gas samples collected over water. So this reaction is kind of an interesting one. It's a side reaction in the formation of methane, actually, from coal. And what they do is they take coal and they heat it with high pressure water vapor, and what they end at high temperature, and they can produce methane from that. But they can also, as a byproduct, produce carbon monoxide and hydrogen gas. Now, hydrogen can be used as a fuel, and carbon monoxide could be as well, except for it's really toxic. So in this particular question, 75.25 milliliters of carbon monoxide gas is collected over water at 50 degrees Celsius and 735.2 millimeters of mercury. How many grams of carbon reacted to produce this gas? So a couple of things you got to pay attention to. If this had not been a collected over water problem, that is, if this had not been said, then this would have been a calculation, directly calculating the moles from the pressure, right, the volume, and the temperature, and all these need to be converted over to the appropriate units. But because it's collected over water, we have to take into account what the partial pressure of water vapor is in this total pressure of 735.2. So let me show you how you would do this problem. To start with, oops, I didn't mean to do that. We need to calculate the pressure of just the carbon monoxide, so 735.2 millimeters of mercury. And then we need to look up the water vapor pressure at 50 degrees Celsius, and what we have at 50 is 92.60 torr. So I'm going to do this, minus 92.60 torr, but I'm going to change that into millimeters of mercury. And it turns out from the very early slide on units, a torr and a millimeter of mercury are about the same. It's 760 millimeters of mercury for an atmosphere and 760 torr for an atmosphere, so they have about the same equivalent unit size, so we can just substitute. So that's going to give me a pressure of 642.6 millimeters of mercury. Now, that's not the unit I need because we know R now is supposed to be an atmosphere, so we'll say 760 millimeters of mercury. That's 1 atmosphere. So when I do that calculation, I'll have 0.8455 borsig figs, in fact, 26. I'll carry a couple of ATM like that. Now my volume is, let's see, 75.25 milliliters. I'll need to convert that over to liters, and it's 10 to the minus 3 liters per milliliter. That'll cancel. And I'll get 7.525 times 10 to the minus 2 liters. And my temperature, again, is not in Kelvin, so I need to get it to Kelvin. It's 50.0 degrees Celsius. I'll add 273.15 to that, and I'll have a temperature of 323.15. Now what I need to do is calculate the number of moles of carbon monoxide. So the moles of carbon monoxide, I'll use the ideal gas law. My pressure is 0.84552.6 atm. Oh, sorry, I should have given you the equation. N is equal to P times V over RT. I just rearranged the ideal gas law. And then my volume is 7.525 times 10 to the minus 2 liters. And then 0.08206 liters times atmospheres over moles times Kelvin. And then T is 323.15. When I do the calculation, that gives me 2.39937 times 10 to the minus third moles of CO, like that. So we're almost done. But now I have moles of CO, and that's where I have to look at my equation. And it's 1 mole of CO for every 1 mole of carbon. So the moles of carbon, actually what I really want is grams of carbon, so I'll just go ahead and write grams of carbon. I'll start with my 2.39937 times 10 to the minus 3 moles of CO times 1 mole of carbon for every 1 mole of CO, and then that times 12.011 actually grams of carbon for every mole of carbon. And then I do that calculate. I get 0.288. Oh, sorry, there's a 0 missing there. 0.02819 grams of carbon, which rounds to 4 significant figures, so I'll have 0.02882 grams. And I just ran out of room. There you go. Okay, so it's really not that different from problems that we've done before, except what you need to do at the very beginning is you need to recognize it says it's collected over water. I often call them CAL problems because that's the abbreviation of collected over water. So you have to recognize it's a CAL problem, and you got to take care of the vapor pressure of water in the total pressure. And then after that, it's ideal gas law. Most of these calculations should be familiar. I know they're long, but should be familiar. And you should calculate the moles of a substance and then figure out where you go from there. Do you need the moles of that substance converted into grams of that substance, or do you need to use some stoichiometry to get it to be equated to another substance, in this case carbon, and then the mass of carbon?